China built an airport that floats on the ocean, not a small airstrip. A massive international hub handling 70 million passengers a year, sitting on land that didn't exist until engineers moved entire mountains into the sea. But that impossible achievement was just the beginning. Across China, 9 airports defy every rule of where airports can be built, and the story starts with the most audacious construction project of them all. You're staring at Hong Kong in 1992, and there's a problem. Hong Kong International Airport. You're staring at Hong Kong in 1992, and there's a problem. The city needs a new airport. The old one sits in the middle of downtown, forcing pilots to thread between skyscrapers at terrifying angles. But there's nowhere to build. Mountains on one side, ocean on the other, zero flat land. So engineers made a decision that sounds insane. They would build an island from scratch, 1,248 hectares where only water existed. Construction crews arrived at 2 tiny islands in the harbor, Chek Lap Kok and Lam Shao, rocky peaks jutting from the sea. They brought explosives and a plan to flatten both completely. The blasting started. Day after day, controlled explosions tore into solid rock. They weren't just leveling peaks, they were obliterating them, turning mountains into gravel. 350 million cubic meters of rock and earth got pulverized. But that material didn't go to waste. Every single cubic meter got dumped into the surrounding ocean. Barge after barge hauling rock into the sea, creating new land, grain by grain. But here's the brutal part. The seabed beneath Hong Kong's harbor is soft. Decades of river sediment creating a foundation of mud and silt. Building runways on that would be like building on quicksand. Engineers drove foundation piles through the sediment, massive steel and concrete columns punching down to bedrock. Some piles went 40 meters deep, thousands of them across the entire site. Then came the seawall, a barrier to hold back the ocean and protect against typhoons that slam into Hong Kong with 100-mile-per-hour winds. They constructed it in sections. Concrete blocks weighing 25 tons each, positioned with millimeter precision. The wall eventually stretched 20 kilometers around the perimeter. But the land inside still wasn't solid enough. The reclaimed earth was settling, compressing under its own weight. Too unstable for runways carrying aircraft weighing hundreds of tons. They used wick drains. Thousands of vertical fabric strips driven into the soil like giant needles. Water squeezed out through the drains, accelerating consolidation that normally takes decades. They compressed 20 years of natural settling into 2 years. Then came surcharge loading, piling extra earth on top of the reclamation to force even more compression. Let it settle. Remove the extra earth. Now the ground could handle anything. 4 years of non-stop construction, 24 hours a day, 40,000 workers at peak, 2 runways where mountains once stood, a terminal larger than any building in the world when it opened, all of it floating on an artificial island in the middle of the sea. But building on water was just one impossible location China would conquer, Dalian Zhoushuizi International Airport. The next challenge wasn't just water, it was cliffs. Dalian sits on China's northeast coast, where steep hills plunge straight into the Yellow Sea. The existing airport clung to this dramatic coastline, but by 2000, it desperately needed expansion. Longer runways for international flights. The problem? Geography had the airport trapped between mountains on one side and ocean on the other. Engineers surveyed the site and saw 2 options. Both impossible. Carve into the coastal hills, blast away millions of tons of rock, or push into the sea, reclaim shallow water to gain length. The terrain was so severe, they couldn't pick one. They did both. Mountain cutting began on the landward side, but this wasn't open terrain. This was an operating airport, with flights landing every 20 minutes. Explosives had to be precisely calculated. Too much force and shock waves damaged the existing runway. They used controlled microblasting. Small charges detonated in sequence. Each explosion fractured rock without creating dangerous vibrations. Excavators moved in immediately after each blast. 30-degree slopes got reduced to level ground. meter by meter. 18 million cubic meters of rock came down. On the ocean side, a different battle was underway. The seabed was shallow but unstable. Silt and sand deposited by coastal currents over thousands of years. They built a containment wall first, a barrier to hold reclaimed material and protect against storm surge from the Yellow Sea. But waves don't stop. Every hour, ocean swells slam into your construction site. They used massive concrete caissons, box-shaped structures 12 meters tall, sunk into the seabed and filled with rocks for weight. Each caisson weighed thousands of tons when filled. Positioning them required split-second precision. Lower too fast and they crack on impact. Too slow and ocean currents push them off target. Crane operators worked in narrow weather windows when seas were calm enough. The caissons interlocked to form a continuous barrier. Then the filling began. Dredging ships sucked sand from deeper waters offshore, pumped it through massive pipelines to the construction site. The slurry of sand and water poured into the area behind the caisson wall. Water drained away. Sand remained, slowly building up land where ocean existed. But dumped sand and silt compress, settle, shift under load. Not good enough for a runway-handling aircraft weighing 400 tons at landing. They used dynamic compaction. Cranes lifted massive concrete weights 20 meters in the air, dropped them. The impact sent shock waves deep into the fill material, crushing voids and forcing particles together. Each drop compacted a column of earth beneath it. They did this across the entire reclaimed area in a grid pattern. The result? A hybrid runway, half carved from mountain, half built on reclaimed sea. 3,600 meters of usable length where geography said it was impossible. One problem solved. But the real engineering madness was just beginning. Beijing Daxing International Airport. By 2014, Beijing had a crisis brewing. Capital International Airport was choking, maxed out capacity. The city needed a second major airport, and they needed it fast. But they didn't want just another terminal. They wanted something the world had never seen. Zaha Hadid's architecture firm presented a design that seemed physically impossible. A starfish. 6 massive curved spokes radiating from a central core. 700,000 square meters under a single roof with almost no internal columns. The entire terminal would be one flowing space. Engineers looked at the design and saw a nightmare. Those curves weren't decorative. They were structural. Every spoke cantilevered outward, carrying its own weight plus the weight of passengers, equipment, and a glass roof. Traditional column and beam construction couldn't handle the geometry. They needed a completely new structural approach. The solution was a steel lattice space frame, a 3-dimensional grid of steel members, each one connected to its neighbors at precise angles. The load distributes across the entire network instead of concentrating on individual beams. But here's the catch. Every connection point in a curved space frame is unique. They couldn't mass-produce identical joints. Each of the 45,000 steel nodes had to be custom fabricated. Computer modeling calculated the exact geometry of every single connection. CNC machines cut and welded each joint to millimeter tolerances. Assembly became a massive 3-dimensional puzzle. Construction started with the central core, a massive concrete structure rising from deep foundations. 40 meters down, workers drove foundation piles through Beijing's low soil to bedrock. The core rose 7 stories above ground. Then the real challenge began. Building the spokes. Each spoke extended over 400 meters from the center. The steel framework had to cantilever outward while maintaining the precise curve Hadid designed. They erected temporary support towers every 30 meters, giant scaffolding holding the steelwork in place until sections connected and became self-supporting. The roof structure went up in sections. Workers assembled small portions of the space frame on the ground, lifted them with cranes, and locked them into position. The curved geometry created another problem. The roof wasn't flat. It undulated in 3 dimensions. Installing glass panels on a curved surface is exponentially harder than on a flat one. Every panel was a different size, a different shape. 4,000 glass panels, each one custom cut to fit its exact location. They used parametric modeling, software that calculated the precise dimensions and curvature of each panel based on its position. Assembly crews used GPS positioning to place each piece. Millimeter-level accuracy across a roof covering 70 football fields. The timeline was savage. Ground broke in 2014. The airport had to open by 2019, 4.5 years to build the world's largest single-terminal building. They used modular prefabrication everywhere possible. Crews working 24-hour shifts, 1,400 days from excavation to opening ceremony. The finished terminal has a walking distance from security to the furthest gate of just 600 meters, in a building covering 700,000 square meters. And China was about to build another one on the coast. Qingdao, Jiaodong International Airport. Qingdao watched Beijing's starfish terminal rise and made a decision. They wanted one too. But Qingdao isn't Beijing. It sits on China's eastern coast, where the Yellow Sea meets unstable alluvial soil deposited over millennia. Building Daxing's radical design here meant solving problems Beijing never faced. The starfish design returns. 5 radiating spokes this time instead of 6. Same curved geometry, same massive cantilevers. But beneath the surface, everything had to change. Beijing sits on relatively stable loess soil. Qingdao's coastal location gives you 40 meters of soft clay and silt before reaching anything resembling bedrock. Those cantilevers extending hundreds of meters? They need foundations that won't shift even a millimeter. Engineers started with soil testing, core samples every 10 meters across the entire site. The data revealed the nightmare they expected. The top 20 meters were essentially compressed mud. They drove 15,000 foundation piles across the terminal footprint. Each pile went 40 meters deep. Steel-reinforced concrete cylinders punched through soft layers until they hit load-bearing strata. But driving piles through saturated soil creates another problem. Displaced water has to go somewhere. It migrates laterally, potentially destabilizing adjacent piles. They used a sequenced driving pattern. Piles installed in a specific order to minimize interference. Monitor soil pressure between each installation. Wait for equilibrium before driving the next one. The pile driving alone took 8 months. Once the foundation was secure, the structural challenge mirrored Beijing's. But Qingdao's engineers had one advantage. They learned from Daxing's construction. Every mistake Beijing made got analyzed and eliminated. The steel fabrication improved. Better parametric modeling reduced the number of unique joints from 45,000 to 39,000. More sophisticated CNC programming meant faster production. They erected the central core faster using slip-form construction. Concrete poured continuously as the formwork jacked upward. The core rose in one continuous pour over 3 weeks. But here's where Qingdao added something Beijing didn't have: a high-speed rail station directly beneath the terminal. Excavating for the rail station while building the terminal above required surgical precision. They dug the basement in sections. Install temporary shoring. Excavate down 15 meters. Build the rail platform. Only then move to the next section. The terminal construction continued overhead the entire time. They used 4-dimensional modeling. Traditional 3D building models with time as the 4th dimension. The software showed exactly where every crew would be working at every hour. The curved glass panels installed 20% faster using improved GPS positioning. Robotic arms handled panel placement for the most complex curved sections. The spoke geometry got optimized. Slightly adjusting the curve angles reduced steel tonnage by 12%. From groundbreaking to opening took 4 years. A terminal nearly as large as Daxing on problematic soil while excavating a rail station underneath. 2 starfish airports proved the design worked at any scale. But China's most brutal challenge wasn't about size or curves. It was about altitude. Daocheng Yading Airport, 14,471 feet above sea level. That's where China decided to build an airport. Daocheng Yading sits on the Tibetan Plateau, the roof of the world. At this altitude, the air has 40% less oxygen than sea level. Workers gasp for breath, doing simple tasks. Equipment loses power. And concrete? Concrete behaves like it's never behaved before. The construction crews arrived in 2012, facing an impossible problem. Concrete needs water to cure. The chemical reaction between cement and water creates the bonds that make concrete hard. But at 14,000 feet, water evaporates before the reaction completes. The thin air and intense UV radiation suck moisture out of freshly poured concrete in minutes. They tried standard concrete mixes first. Every test batch cracked and crumbled. Engineers reformulated the entire mixture, added chemical retarders to slow the curing process, increased water content by 30%. But that created a new problem. Too much water weakens concrete. They compensated with additional cement and specialized admixtures. Even with the new formula, pouring concrete became a race against evaporation. They covered every pore with curing blankets immediately. Thick, insulated sheets trapping moisture against the surface. Workers sprayed water constantly for 72 hours. But concrete was just one battle. The runway sits on permafrost, permanently frozen ground that's been solid for thousands of years. Except permafrost isn't actually permanent when you start building on it. Construction activity generates heat. Vehicle engines, equipment operation. That heat transfers into permafrost and it starts to melt. They installed thermal piles across the entire runway base. These aren't normal foundation piles. They're insulated tubes filled with special fluid. The fluid circulates, pulling heat away from the ground. 1,500 thermal piles driven into the permafrost, each one monitored with temperature sensors. Then came the challenge of actually building at altitude. Diesel engines lose 40% of their power in thin air. Not enough oxygen for complete combustion. They modified every piece of equipment. Supercharged engines forcing more air into combustion chambers. Adjusted fuel mixtures. Even with modifications, everything took twice as long. And the workers? They needed oxygen. Crews worked in 4-hour shifts. Breathe bottled oxygen between shifts. Too much exertion causes altitude sickness. The construction season was brutal too. Snow falls 9 months of the year. Work could only happen during 3 summer months when temperatures climbed above freezing. That meant cramming 12 months of work into 90 days every year to 4 years of 3-month construction windows. The asphalt runway required a completely new formulation. Standard asphalt becomes brittle at extreme altitude. Temperature swings from -40 Fahrenheit at night to 80 degrees during the day shatter normal pavement. They developed high polymer modified asphalt. The finished runway is 3,600 meters long. All of it sitting on frozen ground that wants to melt, built with concrete that doesn't want to cure at an altitude where humans struggle to function. But while Dalian conquered altitude, another impossible location was calling. Shenzhen Baoan International Airport. Back at sea level, Shenzhen had a different problem. The city sits on the Pearl River Delta, a massive estuary where river meets ocean. The entire region is tidal flats, swampland, and shallow water. They needed to reclaim land from the sea. Again. The reclamation started in 1989. They mapped the seabed and found exactly what they feared. 40 feet of soft silt and clay. Below that, more silt. They started with hydraulic fill. Dredging ships pumped sand from offshore into containment areas, building up land layer by layer. But the real challenge was making that loose sand stable enough for buildings and runways. They used surcharge loading on a massive scale, piled earth 12 feet high across the entire reclamation area. The extra weight squeezed water out of the underlying soil, compressing it, but surcharge loading is slow. Enter vacuum consolidation. They spread a giant membrane across sections of reclaimed land, sealed the edges, pumped air out from beneath the membrane, creating a vacuum that sucked water from deep in the soil. Combined with surcharge loading, this compressed the ground in months instead of years. But even that wasn't enough for the heaviest structures. The main terminal would weigh hundreds of thousands of tons. They installed stone columns across the terminal footprint. Drilling rigs punched holes 15 feet deep into the soft soil, filled them with crushed rock. Then came the foundation work. They built a massive raft foundation, a continuous concrete slab 3 feet thick, spreading the terminal's weight across the entire footprint. The terminal design itself pushed boundaries. A 1,500-foot-long concourse connecting satellites to the main terminal, too long to build with traditional columns. They used a honeycomb steel space frame. The space frame created a column-free interior spanning the entire length. The roof used another innovation, double-curved glass panels creating a flowing organic shape. But unlike the starfish terminals, this roof had to cantilever over roads and taxiways, parts of the structure extending 60 feet beyond the last support column. They achieved this with post-tensioned concrete beams, steel cables running through concrete, pulled tight after the concrete cured. The tension in the cables creates compression in the concrete, making it stronger. The reclaimed land totaled 800 acres, all of it built on what was open water and tidal flats. And Shenzhen proved that sea level reclamation could be perfected. But Shanghai was about to take it even further. Shanghai Pudong International Airport. Shanghai Pudong opened in 1999 on reclaimed wetlands. But the original airport was just the beginning. Over the next 2 decades, they would build 3 more runways. Each one on progressively worse soil. Each one while the airport operated at full capacity. The expansion site sat on coastal wetlands, water table just 3 feet below surface. The soil profile showed weak clay layers extending 80 feet down. They started with the 3rd runway in 2005. The ground improvement operation was brutal. They used vertical drains across the entire runway footprint. Fabric strips driven 60 feet into the clay at 6-foot intervals. 50,000 drains per runway. Then vacuum consolidation, pumping air out to create negative pressure in the soil. Water migrated to the drains and got extracted. The clay compressed as water left. The consolidation took 18 months per runway. Constant monitoring of settlement. While the ground consolidated, they prepared for the next phase. Stone columns. They installed them in a grid pattern across the runway. Each column, 18 inches in diameter, driven 60 feet deep. The installation used vibration. A vibrating poker drove down into soft soil, displacing it. Crushed stone poured in as the poker withdrew. 20,000 stone columns per runway, each one transferring load from the runway down to deeper, more stable soil layers. But here's where Shanghai's expansion got truly complex. The 4th runway, built in 2020, sat even closer to the coast. The water table was higher. The clay was softer. Standard ground treatment wouldn't be enough. They used deep cement mixing, a technique that literally turns soil into concrete underground. Mixing rigs drilled down 80 feet, injected cement slurry while spinning augers mixed it with the clay, creating underground concrete columns without excavating anything. 500 cement soil columns per acre, arranged in a grid, creating an underground wall of reinforced ground. The construction sequencing was surgical. They built new runways while 3 existing runways handled 800 flights daily. They created temporary taxiways routing traffic around construction. The entire expansion required moving 60 million cubic yards of material, installing 175,000 vertical drains, driving 80,000 stone columns, creating 40,000 cement soil columns, all while the airport never stopped operating. The future was calling from the mountains of Sichuan. Chengdu Tianfu International Airport. Chengdu sits in a mountain valley in Sichuan province. By 2015, the existing airport was maxed out. They needed a new one. But the only suitable location was a valley floor with 300-foot elevation changes across the site. The design returned to the starfish concept, but this time they built 2 of them. Twin terminals shaped like phoenixes. Each one 600,000 square meters. Mirror images facing each other across the airfield. The earthwork challenge was staggering. They needed to create a level platform for runways and terminals in terrain that rose and fell dramatically. 280 million cubic yards of earth had to be moved. They started with surveying, mapping every contour across the 20 square mile site. Computer modeling calculated optimal cut and fill zones. The grading plan called for cutting hilltops down 150 feet in some areas, filling valleys with 100 feet of compacted earth in others. The excavation used a fleet of heavy equipment, 200 excavators, 300 haul trucks, operating continuously. The fill zones required precision compaction, dumped earth, spread in 8-inch layers, compacted with vibratory rollers, tested for density. Drainage was critical. Water running off surrounding mountains had to be redirected. They built channels diverting flow around the construction site. One miscalculation and flash floods could wash away months of work. The terminal foundation started once the platform was stable. But here's where Chengdu innovated beyond previous starfish designs. They synchronized construction of both terminals. Two identical structures rising simultaneously. They divided labor into specialized teams. One team fabricated steel for Terminal 1. An identical team worked on Terminal 2. Same schedule, same sequence. Any lesson learned on one terminal immediately applied to the other. The curved roof structure used parametric modeling refined from Qingdao's experience. Computer software generated fabrication drawings for every steel member. CNC machines cut components. Assembly crews bolted them together on site. The precision meant zero field modifications. Each terminal used 35,000 tons of steel in the roof structure, 70,000 tons total. But the real innovation was below ground. Each terminal connected to an underground transportation hub, high-speed rail, metro lines, parking garages, all excavated beneath the braes. Terminals, while construction continued above. They used top-down construction. Build the terminal basement roof first. Use it as a working platform. Excavate beneath it, while building the terminal structure above. 4 years, from groundbreaking to opening. Twin terminals, larger than most airports' entire footprints.